Hello viewers, in this video I am going to present the operation of monostable multivibrator. As name implies, it has one stable state and one quasi-stable state. When an external trigger pulse is applied, the circuit changes its state from stable state to quasi-stable state. Then the circuit returns back to the stable state automatically after a short time interval t, as we discussed in the previous lecture. Before going into the topic, let me introduce the most important keywords of the multivibrators. They are state, stable state and quasi-stable state. State is actually voltage levels. They are high level and low level. High level means plus VCC, which is 12 volt for transistorized electronic circuits, and low level is 0 volt. In either way, it can be called as logic 1 and logic 0 in terms of digital electronics. The second one is stable state. Multivibrator will stay in this state indefinitely until the trigger pulse is applied. The third one is quasi-stable state. This is actually temporary stable state or unstable state. The circuit will stay at this state for short time interval t. To understand the operation of multivibrators better, we will see the switching properties of the transistor. Now let us find what are the output voltage and output current when one transistor is at off state as well as an on state. First we'll see when a transistor is at off state. When the input voltage applied between base and emitter junction of the transistor is less than the cut-in voltage, which is 0.7 volt for silicon and 0.3 volt for germanium, then the transistor goes to off state, which means the collector and emitter terminals are open circuited. So, no current will be flowing through the collector terminal. So, IC equal to 0. The voltage across the collector to emitter terminal VCE equal to VCC. Since the collector and the emitter terminals are open circuited, the entire power supply voltage will be appeared across the output terminal. Let me summarize this. When a transistor is at off state, the collector and the emitter terminals are open circuited. The collector current is equal to 0. The collector to emitter voltage is equal to VCC. Next we'll see the output voltage and output current when a transistor is at on state. When the input voltage applied between base and emitter junction of the transistor is greater than the cut-in voltage, the transistor goes to on state, which means the collector and emitter terminals of the transistor are getting shorted. So, more current will be flowing through the collector terminal, which is equal to IC saturation. The voltage across the collector to emitter terminal will be equal to 0 since the voltage across the short circuited terminal is 0. Let me summarize this. When a transistor is at on state, the collector and emitter terminals are short circuited. The collector current is equal to IC saturation. The collector to emitter voltage equal to 0, which is equal to VCE saturation practically. Now we will see how the monostable multivibrator is functioning. In the circuit diagram, we can see two transistors Q1 and Q2 are cross-coupled. The collector of the transistor 1 is coupled to the base of the transistor 2 through the capacitor C1, and the collector of the transistor 2 is coupled to the base of the transistor 1 through the resistor R2. This capacitive coupling is called AC coupling and this resistive coupling is called DC coupling. The resistor RL1 is the load resistor of the transistor 1. The resistor RL2 is the load resistor of the transistor 2. The components R1 and C1 are used to determine the pulse width of the monostable multivibrator. The minus VBB is given to the base of the transistor 1 to keep the transistor 1 in reverse bias condition. The capacitor C2 is connected to the base of the transistor 1 through which a positive going trigger pulse is applied to the base of the transistor 1 whenever it is needed for monostable multivibrator to switch from stable state to quasi-stable state. When the power supply is switched on, transistor 1 will be at off state because minus VBB is given to the p-type base, so it gives the reverse bias to the transistor 1. So the transistor 1 will be going to off state. Once it is off, the collector and emitter terminals are getting open circuited. So, no current will be flowing through the collector terminal, which is equal to 0. The voltage across the collector to emitter terminal will be equal to VCC. At the same time, the supply voltage VCC will be applied to the base of the transistor 2 directly through the resistor R1. This supply voltage is much greater than the cut-in voltage of the transistor 2, so that the transistor 2 will be driven to on state. Once it is on, the collector and emitter terminals of the transistor 2 are getting shorted. So, more current will be flowing through the collector terminal, which is equal to ICE saturation. The voltage across the collector to emitter terminal will be equal to VCE saturation. This is the stable state of the monostable multivibrator, which is Q1 off and Q2 on. During the stable state of the monostable multivibrator, the output of the monostable multivibrator, which is taken across the collector to emitter terminal of the transistor 2, is at VCE saturation, which means this stays at logic 0 level. The circuit will stay at this stable state indefinitely. When we want to switch from logic 0 level to logic 1, an external trigger pulse is to be applied. Now we will apply a positive going trigger pulse of sufficient magnitude and duration to a base of the transistor 1. Since this positive pulse is applied to the p-type material, this forward biases the transistor 1. So the transistor 1 will be driven to on state. Once it is on, the collector and emitter terminals are getting shorted. So more current will be flowing through the collector terminal, which is equal to IC saturation. So the voltage across the collector to emitter terminal will be VCE saturation. This voltage is almost 0, which is applied to the base of the transistor 2. So this will not keep the transistor 2 in on state. So this will bring the transistor 2 from on to off state. Once it is off, the collector and emitter terminals are getting open circuited. So no current will be flowing through the collector terminal, which is equal to 0. So collector to emitter voltage will be equal to VCC. This is the quasi-stable state of the monostable multivibrator, which is Q1 on and Q2 off. During the quasi-stable state, the output of the monostable multivibrator will be switched from 0 to 1. The circuit will stay at this quasi-stable state for short time interval T. And now the capacitor C1 starts charging towards VCC through R1, C1 and Q1, with the positive polarity in the right side of the capacitor and negative polarity in the left side of the capacitor. As capacitor charges towards VCC, the voltage of the capacitor increases step by step from 0 to VCC as 0.1, 0.2, 0.3 up to VCC. When the voltage of the capacitor reaches the cut-in voltage of the transistor 2, the transistor 2 will be driven to on state. Once it is on, the collector and emitter terminals are getting shorted. The voltage across the collector to emitter terminal will be equal to VCE saturation. This is almost 0, which is coupled to the base of the transistor 1. So this is not at all sufficient to keep the transistor 1 in on state. So it will switch the transistor 1 from on to off state. Once it is off, the collector and emitter terminals are getting open circuited. So no current will be flowing through the collector terminal, which is equal to 0. The voltage across the collector to emitter terminal will be equal to VCC. Now the circuit is returned back to its stable state. The time taken for the capacitor to charge from 0 volt to cut-in voltage of the transistor 2 is called as T, which is 0.69 R1C1 for monostable multivibrator. Since a single pulse is used to make transition from one state to other, this multivibrator is also called as one-shot vibrator or univibrator. To draw the collector and base voltages of transistor 1 and transistor 2, I have mentioned the stable state in the first time slot where Q1 is off and Q2 is on. The second time slot is for quasi-stable state where Q1 on and Q2 off. The third slot is for stable state. The first graph refers to the base voltage of the transistor 2, which is VB2. The second graph refers to the collector voltage of the transistor 1, which is VC1. The third graph is drawn for the collector voltage of the transistor 2, which is VC2. The fourth graph is drawn for the base voltage of the transistor 1, which is VB1. First we'll see how to draw the collector voltage of the transistor 1. During the stable state, the transistor 1 is at off state and the output voltage of the transistor 1 is VCC. So, the output of the transistor 1 will be at VCC. And during the quasi-stable state, the transistor 1 is at on state and the output voltage of the transistor 1 is VCE saturation. So the output of the transistor 1 will be switched from VCC to VCE saturation. During the stable state, the transistor 1 is at off state and the output voltage is equal to VCC. So the output of the transistor 1 will be switched back to VCC. Next we will see how to draw the collector voltage of the transistor 2. During the stable state, the transistor 2 is at on state and the output voltage of the monostable multivibrator is VCE saturation. So the circuit will stay at VCE saturation. During the quasi-stable state, the transistor 2 is at off state and the output voltage is equal to VCC. So the circuit will be switched from VCE saturation to VCC. During the stable state, the voltage of the transistor 2 is VCE saturation. So the circuit will be switched back to VCE saturation. Next we will see how to draw the base voltage of the transistor 2. During the stable state, the transistor 2 is at on state. When a transistor is at on state, the collector voltage will be equal to VCE saturation and collector current will be equal to ICE saturation, and thus base voltage is equal to VBE saturation. So here we can see the VB2 saturation is drawn for the stable state. And for the quasi-stable state, the transistor 2 is at off state. When the transistor 2 is at off state, the transistor 1 must be in on state. So the voltage at this point is VCE saturation. The voltage at this point is equal to the supply voltage VCC. The capacitor voltage is now equal to VCC minus VCE saturation, which is coupled to the base of the transistor 2. So the voltage level is mentioned here, which is VCC minus VCE2 saturation. This curve shows the capacitor curve. And during the stable state, the transistor 2 is at on state. When this is at on state, the base voltage is equal to VB2 saturation. Next we will see how to draw the base voltage of the transistor 1. During the stable state, the transistor 1 is at off state. When the transistor 1 is at off state, we should find out what is the voltage at this point. To find the base voltage of the transistor 1, we should take the VC2 also into account, since the collector of the transistor 2 is connected to the base of the transistor 1. Between this point and this point, by applying the superposition principle, we can find the voltage at this point, which is much lesser than the cut-in voltage. So that voltage will be shown in this stable state of the VB1. During the quasi-stable state, the transistor 1 is at on state. When the transistor 1 is at on state, the base voltage is equal to VBE1 saturation, which is shown here. And during the stable state, the transistor 1 is at off state. So the voltage of this slot is equal to the voltage of the first slot. Next we will see the applications of monostable multivibrator. As pulse width of monostable multivibrator is adjustable, we can use monostable multivibrator to produce rectangular waveform, and hence it can be used as gating circuit. And also it can be used to introduce time delays. Monostable multivibrators are used in analog systems to control an output signal frequency. They are used to synchronize the line and frame rate of television broadcasts. Monostable multivibrators are used to moderate the tunes of different octaves with electronic organs. Thank you.